Let's get started. So I think up to this point, I've assigned like up to 56, although I think last time I told you probably can't do past 42 or 43 or something like that. Before we get started, I'll take questions if anybody has anything. Again, anything up to 56 is fair game, but it could be something real old that's still okay. Wade?
Can you do anything on a build test?
Sure. Let's see. All right, let's look here. That's not what I want. Let's do that. Okay. So you want to talk about one of these guys, right?
Yeah.
Okay. It says the function f of x equals the absolute value of x minus 3 can be used to determine how far away or how far a number x is away from the number 3 on the number line. Find and interpret the given function values and determine an appropriate domain for the function. So f of negative 5, if I plug negative 5 in here, I get positive 8, right? Negative 5 minus 3 is negative 8, and then I do the absolute value, makes it positive, which means that the number negative 5 is 8 units away from 3 on the number line. Well, that makes sense, right? If I put negative 5 on here and I count, that's 8 units. F of 1, well, that should be 2. 1 minus 3 is negative 3, and the absolute value makes that positive 2. So that tells me the number 1 is 2 units away from 3, and obviously that makes sense. And then 1.5 minus 3 is negative 1.5, but then the absolute value makes that positive. So that tells me that the number 1.5 is 1.5 away. And again, that should make sense because all we're talking about is a distance, right? If I pull out 1.5, that's here. That's 1.5 units still, right? So based on here, the domain should be, I can put in negative numbers, positive numbers, decimals. All of that is fine. That all makes sense. So that should tell me everything is in the domain. So I'll pick all real numbers for that. Dominic Garrick, for you. So let's do another one that's a little less, or maybe a little less obvious, right? In a board game, a certain number of points is awarded to a player upon rolling a 6-sided die that is labeled 1 to 6. According to the function f of x equals 4x minus 4, where x is the value rolled on the die. Find and interpret the given function values and determine an appropriate domain for the function. Okay, so f of 4, if I plug 4 and I have 4 times 4 is 16, minus 4 is 12. So that means when a 4 is rolled, the player is awarded 12 points. Well, that makes sense because I can roll a 4. If I do 5.5, 5.5 times 4 is 22, and then minus 4 is 18, meaning when a 5.5 is rolled, we are awarded 18 points. But that doesn't make any sense at all because I can't roll a 5.5 on a 6-sided die. If I do f of 10, that's 40 minus 4, so that's 36. So when a 10 is rolled, I'm awarded 36 points. But that doesn't make a lick of sense either because my 6-sided die certainly doesn't have the number 10 on it. So an appropriate domain is going to be, well, I can only get the numbers 1, 2, 3, 4, 5, and 6, right? So those are all integers. So the lowest could be 1, and the highest would be 6. So I just want the integers 1 to 6. So that's kind of what we're doing, right? So you're just kind of pushing through the, the number through the function, writing that, like, what do these numbers mean, the input and the output, and then determining, like, is that a reasonable number that I could plug in, or does that output kind of make sense in the context of the story that they gave you at the beginning, right? So you really have to read that beginning part and, like, understand what x and f of x are representing to answer that. Does that?
Yeah, that helps.
That helps? Does everybody else kind of get what we're doing there? Seeing an example or two makes that probably a whole lot clearer. Okay. Well, that was a good one to ask about. Lots of people, it seemed like, didn't finish the delta math. Probably this section in particular, I didn't look at exactly what you didn't finish other than your percent completed or whatever. But when I see 83, it's clear that one section didn't get done. That would have been my guess as the section that didn't get done. But that's fine. Again, if you still have stuff to finish on there, you can complete that and send me an email when you're done. I can go back and recheck. Okay? Other stuff from homeworks that you guys want to talk about? Jacob. 20 or 21? Yeah, sure thing. Which one? Do you have a preference there? 20? Sure thing, dude. All right. So if I do 20, I'm going to just start by, I guess the H is the name. I know that whether I'm doing odd or even or neither, I always got to start just by plugging negative x in. So if I do that, I'm just going to replace all the regular x's with negative x's. And now I'm just going to simplify. So negative of negative x squared, how many negatives is that? 3, right? There's 1 for the negative out front, and then there's 2 because we have a negative squared, right? So 3 total negatives, so that should be negative. And then x squared. And then plus a negative x is the same thing as minus x, minus 1. Well, I see that that's definitely not h of x because this one has a minus x, h of x has plus x. And if I factor a negative sign out of this, that's definitely not negative h of x because h of x, this should be negative, right? So since it's neither, we know that we're not even because of this, and we know we're not odd because of that. Therefore, we'd say it's neither. Does that feel okay, Jacob? Zoom out there for us a little bit. Grace?
What about the 2 negatives like cancel
out? Well, there's actually 3 negatives here. So this is 1. And then because this negative is squared, there's actually 3 negatives there, right? Because you would think about it as like negative times negative x times negative x. So there's actually 3 negatives there. That's why it's negative. And now that's easy to miss, right? A lot of us want to do the cancel the 2 negatives and then square. Exponents come before multiplication, right?
You factor the negative, does the minus 1 have
Oh, yeah, it should be plus 1. Yeah, sure. That's still an issue though, right? Yes, but thank you. That's 100%. Still not odd, but yes, I did goof that for sure. Thank you. Wade.
Can you do 23?
Sure. Uh-oh. All right, so here we're asking for the vertical and horizontal asymptotes, and I'm I'm going to justify those answers by creating a table, kind of the same way I would ask you guys to do in your on the test or whatever. So I'm going to start by typing in the function into my calculator so I can look for the location of those asymptotes. So I'm going to type this in exactly as it's written. So I want that vertical fraction or horizontal fraction bar. To get that, I do alpha and then y equals and pick that very first option. And now I can just type in exactly like it looks like on my sheet of paper. And then I graph stuff all the time in class, so I don't know what my last window was. And rather than going and looking, I'm just going to pick Z standard, and that resets my window back to kind of the default, which is usually probably going to be fine. I'm always going to look at whatever that is first before I start adjusting, unless I know for certain, like I know exactly what I want. So if I look at this, let's see, I see a vertical asymptote like right here. That looks like it's at about 1. And then for my horizontal, it looks like, again, I right about here, which also looks like 1. Remember, for vertical lines, they rewrite them x equals, and for horizontal lines, we write them y equals. So now I'm going to build an XY table to kind of check these. I'm going to verify this with my calculator. So here I want to pick some values that are getting closer and closer to positive 1. So I'm going to start with some numbers that are less than positive 1, but getting closer and closer. So maybe like 0.9, 0.99, and 0.999. And then we'll do some numbers that are a little bit bigger than 1, but still getting closer to 1. So like 1.1, 1.01, and 1.001. That should supposed to be an O. So far, so good. And now I'm just going to punch these numbers into my calculator, plugging them in for x. Now I'm not going to do this by hand. I'm rather going to ask the calculator to do it for me to just save myself a lot of button pushing. So what I want to do is I want to get the Y1 command. To get that, I'm going to press the vars button, which is right here underneath the down arrow. And then since we're looking for the Y1, I'm going to go to the Y vars. And I'm going to choose the function option because that's the mode our calculator's in. And then I'm going to pick the Y1 because that's where I typed in the equation into my calculator. So then I'm going to do a parenthesis, like it's a function notation, and then we're just going to plug 0.9 in. So there's an answer. And I'll press second and enter. That recalls the last thing I typed in. So I can just go back and edit that without having to jump through all those menus again. It just saves myself some buttons. And I do it again. So if I write those down in my table, -9, -99, -999. To me, it looks like these y values keep getting smaller and smaller without bound. So that tells me it's going to -infinity. I'll do the same thing now for these other three. So again, I'll just press second and enter. I'll go back and update this for 1.1, and then 1.01, and then 001, and I notice kind of the same behavior, but this time in the opposite direction where these are getting bigger and bigger without bound. So that tells me it's going to positive infinity. These two are what indicate that it's a vertical asymptote, seeing that on either side we're heading to an infinity, either positive or negative. They could be both the same. They could be both different. It doesn't matter which one happens first. Now for the horizontal asymptote, this will be a little bit different because here our graph is approaching a y value. When we get to the far ends of the graph, like over here and over here, we're approaching a specific y value. So what I want, rather than picking x's that are getting closer and closer to some number, I want x's that are getting like arbitrarily small or arbitrarily big. So for small, I'll just do like -10, negative 100, negative 1,000. And for x's, I'm just going to do positive 10, positive 100, positive 1,000. So I'll do the same thing. I'll just press second and enter and just go back and edit what I have here so I don't have to jump through all those menus again to get that y1 back. And now, don't love that. I prefer not to get a fraction. A decimal would be much more meaningful for me here. So what I'm going to do is I'm going to tack on to the end of this, press math, and then I'll do the decimal command. God bless you. So that forces the calculator to give me an answer as a decimal. And I'll just second and enter, go back and fill this in. Now I want to be careful here because I don't want to overwrite the parentheses and have to recall that decimal thing again. So instead I'll do second and delete. Notice my cursor changed from flashing black to flashing white. That's going to allow me to add in a digit without erasing anything. It's like inserting that number in there. So that's what I want to do rather than overwriting what I had there. So that gives me 1.01. And then do the same thing. I'll insert that 1,000 in there. And I have 1.001. And again, what am I seeing here? We're getting closer and closer to 1, right? If I go and oops, I put these in the wrong spot though. Goodness gracious, Mr. Kulik. We're just going to do that. That's easier than erasing and rewriting. So now let's do the negatives. So I'll just go and recall this last thing. I'm going to insert a negative sign out front. And I'm going to start with negative 1,000. Because if I do it that way, I don't have to do that insert anymore. I can just like add in the number or delete out the value at the end, and I don't have to do any mumbo jumbo there. So I get that, 9999. And then we'll recall that and get rid of the 0. And here I have 0.99. And then recall that and get rid of a 0. And that gives me 0.9. And again here, we're getting closer and closer to 1. And since these are agreeing to the same value, that's the horizontal asymptote part. Does that feel okay? I know I raced through some of that. It's just like getting used to doing the stuff on your calculator, right? Yes, yeah. And again, the nice part about this is all recorded if you needed to go back and like, okay, I need to actually follow along with my own calculator now and do this because like to get used to where these buttons are and where the commands are inside of these menus, I got to do it for myself. You can always go back and watch the video and just kind of pause. When you look at it, like wherever my cursor is going is like highlighted, so it's kind of easy to see. Everybody cool? Grace? 41? Sure. All right, so 41 asks, has a bunch of parts to it. So the first part, part A, asks, is this a function or not? Well, no, right? Fails a vertical line test. That's real easy. Part B asks for its domain and range. So the domain, I'm going to go and find the point with the smallest x coordinate. That is the point that's furthest to the left. Looks like it's maybe that one that starts at -6. So that would be like my lower bound. And then my biggest one looks like over here at +10. Now it certainly looks like the point -6, -1 is a point on my function, so I'll give that a bracket. It looks like there's one that 10, -1 would be a point on my function, so I'll give that a bracket. Now for the range, I'm going to locate the the lowest point on my function, which looks like it's probably here at 2, -5. And the highest point on my function, it looks like it's here at 3. And again, both those look like y coordinates on my function, so I'll write those in with brackets. Does that feel okay so far? Part C asks, is this one-to-one? Well, that should be easy. No, like again, we fail a horizontal line test. That's my test for one-to-one. Yes?
How do you know if you have brackets?
So, because I actually have the point that uses that x-coordinate -6, that's why I'm using a bracket there, because that is actually a number that's a point on my function.
Okay.
Okay.
So horizontal line test fails to one-to-one.
One-to-one, their test for that is a horizontal line test.
Is there like a test for another one?
Another test for one-to-one?
For the other type of.
Vertical line test? Test for a function or not.
For onto.
Well, if what you're given is a graph, it's got to be onto. The only representation I could give you that I can draw something that's not onto is like one of those mapping diagrams. So you don't have to worry about the onto part. If you're given a equation or a graph, the onto part can be assumed. Okay. Good question though, right? The predictive and inverse relation is a function or not. We'd say not. And since f is not one-to-one, f inverse is not a function. And then part E asks us to draw in the graph for this, or the graph for the inverse here. So to do that, I'm just going to observe that I'm going to use these 4 points that are kind of the highest and lowest, furthest left and furthest right points on this ellipse, this oval. And now I'm just going to transpose those points to create the points for my inverse. So -6, -1 becomes -1, -6. That goes here though. And then 2, 3 becomes 3, 2. And then 2, -5 becomes -5, 2. And then 10, -1 becomes -1, 10. And if I kind of just connect those, there's my inverse. And ideally, you can draw a better ellipse than I can on the computer screen, which is kind of tough to draw that, but it's supposed to look like an ellipse, not a lumpy circle like I've drawn here, but yeah, we'll take it. Does that make sense though, Grace, on what I did there? Okay. Again, as I'm doing these things, like if I'm going too fast or there's a follow-up or I said something you didn't catch or whatever, you can stop and ask me, like, can you say that again? Can you slow down? Like, hold on, I didn't catch that. Can you do that part again? Any of those things are fine. Sometimes I just get excited and really you know?
So if it wasn't one-to-one, it would, like, that inverse of that would be a function.
One-to-one is a necessary condition for an inverse to be a function. Have to have that in F for F inverse to be a function. Okay. Let's pick up where we left off in 1.7. Try to finish that up here today. So where we left off, we had been talking about writing inverses for functions, and we had done this example here. I'm going to redo this example now to kind of start today. So the steps for writing the inverse of a function are as follows. The first thing I want to do is rewrite my function without the function notation. So I'm just going to replace the f of x with a y equals. And the steps I'm going to describe are identical for any situation, but the details can change depending on the type of function we have. The next step I want to do is to get the x by itself. So to do that, we'll add 7 to both sides. And then divide both sides by 3. And again, when I write this y plus 7 all over 3, you could also write it as like y over 3 plus 7 over 3. That's fine. Whether you write it as a common denominator as two separate fractions, either is okay. So now the x is by itself. Step 3 would be to rewrite this by swapping the x and y coordinates. So all of my x's I'm going to rewrite as y's, and all of my y's I'm going to rewrite as x's. And then the final step would be putting this back into function notation. This time I'm going to replace the y with f inverse of x. And so there is my inverse, right? So again, the 4 steps. We write the function notation as a y equals. Get x by itself, that's usually the hard one. Swap the x's and y's, and then put it back into function notation, writing, f inverse or whatever the name of your function is. Okay, so I have what I think is my answer, my inverse. How do I know that that's correct? How do I check that? Well, better than graphing, I have another option where instead of it being graphical, we can do this without needing a calculator, right? Because to graph this, you kind of need the calculator to do that, right? Or else it becomes rather time-consuming and in some cases really difficult, right? Because not all graphing are going to be as trivial as graphing 2 lines, which we're doing here. Although that is a reasonable answer. I'd remind us of our definition of inverses that we talked about last time. So remember that when we defined an inverse, we said that it was just the 2 things are inverses if the composition both ways simplify down to x, right? Let's do that then for this f and f inverse that we just found. So I have to check 2 things. I have to check f compose g. And I remember that my definition of composition just tells me f compose g is f of g of x. And my g of x in this case is, I don't know why I wrote it differently than my answer was before, but I did for whatever reason. I wrote it this time as 2 separate fractions rather than 1 big fraction, but like, hey, we just talked about how that means the same thing, right? So what does it mean when I write f of 1/3 x plus 7/3? Well, it really means that I'm going to take that and plug it into the x, right? So I have the 3, and instead of the x, I'm going to write 1/3 x plus 7, and then I still have that minus 7 afterwards. So far, so good. Okay, now I just need to simplify. The first thing I should do to simplify this is distribute the 3. Yes, good. So 3 times 1/3 is 1. So that just gives me 1x. I'm going to write x instead. 3 times 7/3 is 7. And then I still have that minus 7 at the end. I notice that plus 7 and minus 7, those just cancel each other out. And there's the x that I was hoping to get. Yay!
Yes.
Now we have to do the other direction though, right? So we also have to do that way. Okay. Well, it's going to feel quite similar. Except here, we're going to be taking the 3x minus 7 and plugging it into the x. So I'm going to have 1/3, and then instead of x, I'll have 3x minus 7, and then I have that plus 7/3. Simplifying, so to start the same way, distribute the 1/3 through. 3 times 1/3 is just 1, so I have an x there. And then 1/3 times 7 is just 7/3. And I have the plus 7/3. Cancel each other out. That gives me x. And I'm done. I'm convinced that these two things are actually inverse of each other, because when I do the composition both ways, it all simplifies down to x. The rest of today, we're going to just be doing more and more algebraic examples like this. Gives me the opportunity to review some techniques that we should remember from Algebra 2 and some basic algebra vocabulary, which is a great thing to be doing here at the start of the semester as we're kind of getting our feet wet again, thinking about mathematics, because, well, it's been a little bit of time since we've probably thought deeply about these ideas. Okay. So let's look at our next example here. So again, same instructions. We're just finding the inverse. What do we notice immediately about the function h of x here that's different than the previous one? Does anybody notice anything immediately different that's going to make this a little bit harder? Anybody want to take a risk and just throw out a guess? Look at the x's. How many locations do I have x in? 2. I have 2 separate x's in this. That's going to make life a little bit more complicated, right? So that's going to be the first piece. That's what I'd want to notice about this right away. So my first step, finding the inverse, I'm going to replace the function notation with y equals. And now I want to get the x by itself. But which x? Well, the answer is I have to get those two x's combined into one place before I can get the x by itself, right? So that's going to be my first order of business, is try to get these two separate x's together into one place. What should I do to start that process? What do we think? I would start by just getting rid of the fraction. How would I do that? Great, multiply both sides by 5x minus 8, the denominator, right? So when I multiply that to the right side, the 5x minus 8s cancel out. And on the left side, we're just going to distribute the y through. So far, so good. Now, we're trying to get these x's into one place so that I can get the x by itself, right? So the next thing I'm going to do is I'm going to get the x's all onto one side and the stuff without the x's on it to the other side. Now I have 5xy minus 2x. Are those like terms? No. Can I just subtract them together all willy-nilly? Definitely not, right? Because they're not like terms. How would I do that then? 5xy minus 2x. Well, I just write them next to each other, right? Isn't that what we do? If they're not like terms, you can't combine them together. You just write the thing. Same thing going on with the 5 and the 8y. So again, I'll just write them next to each other. So now we have the x's alone on one side. How am I going to get that x that's in two different locations into one single location? This is a technique that you've used before, probably last year in Algebra 2, the year before in Algebra, probably prior to that in pre-algebra. It's an old technique that you should remember, but it's a weird context to use this in. It is factoring, great. Specifically, what kind of factoring? Yeah, so there's like when we undo foiling, where you like multiplies to give us and adds to give us. And then there's something like this, where what you're looking for is the greatest common factor. If I look at 5xy and 2x, the greatest common factor is x. So I can factor that x out front, leaving me with 5y minus 2. And now instead of having two separate x's, I have just one x. Yes! Now, again, we're trying to get the x by itself. We had to get the two separate x's into one place to do that, but that's where we're trying to go. So I have to get that 5x or 5y minus 2 out of there. How am I going to get rid of that part? What? Yeah. So the operation going on between the x and the 5y minus 2 is multiplication. To undo that, we're just going to divide both sides. leaving us with x equals 8y plus 5 over 5y minus 2. Well, x by itself. Step 2, finished. Next, I swap the x's and y's. So everywhere there was an x, I write a y. And then everywhere there was a y, I write x. And then I return this to function notation. Our original problem wrote h of x equals, so here we found h inverse of x. What's up? No? Oh, okay. I thought I heard excuse. I thought you were trying to ask something. You're good? Okay. Now that was a little bit more complicated than the previous one, right? Not impossible, but specifically going from this step to this step was a little bit of a stretch for us, right? But once we've seen that trick, that helps. I can recognize that now in the future when I have a problem with more than one x in it, that at some point I'm going to have to do a factoring to kind of get that x from one or from two locations to one location. So far, so good? Okay. What if I want to check this, though? Right? We have to do these compositions. Now, I want to warn you in advance. This one's pretty nasty. The algebra is a little rough here, so just kind of roll with me for a minute. So, definition of composition means that that is h of h inverse. And we just found that h inverse was 8x plus 5 over 5x minus 2. So when I plug that into h, I'm going to have 2x, but instead of x, I'm going to write that fraction, h inverse, and then I have the plus 5, and that's all over 5x, but instead of x, I'm going to write that fraction, h inverse, and then a minus 8. And take a look at that gross looking thing. Anybody remember from last year what we call that when you have like a fraction inside of a fraction like that? We call that a complex fraction. Do you remember what we call something that looks like this? Where we have like a fraction with x's in it like this. Starts with an r, do you remember? It's a rational function where we have a polynomial divided by another polynomial. Thank you. Dominic, G for you. You're a popular guy this period.
Yeah.
Anyways, that guy is a rational function. A rational function is just a polynomial divided by another polynomial. Just kind of reviewing some vocab as we're going. All right. So, remember, we are here. We want to simplify this now. To simplify a complex fraction, there's really two strategies. The first strategy is I can simplify the entire numerator down to a single fraction. and then simplify the entire denominator down to a single fraction, and then divide the two fractions. Blech! That's not what we're going to do. I think that algebraically that's a lot more symbol pushing than the alternative. The alternative is, what we're going to do is we're going to clear out the little fraction inside by multiplying the top and bottom, or just multiplying this big fraction by 1. So remember, when we make a common denominator, we multiply the top and bottom of the fraction by like 5 on top and 5 on bottom. And it's okay to do that because all we're doing is just multiplying by 1. We're going to do the same idea here, but we're going to choose our 1 carefully. What we want to do is we want to look at all the denominators in our problem. So the denominators I see are 5x minus 2, a 1, a 5x minus 2, and another 1. And what I want to find is the least common multiple of all of those denominators. So what is the least common multiple, the LCM of 5x minus 2, 1, 5x minus 2, and 1? It's not 1 because 1 isn't a multiple of 5x minus 2. It's just 5x minus 2. So now when I'm going to distribute this through to the top and bottom of my fraction, what happens when I multiply 5x minus 2 with the fraction 8x plus 5 over 5x minus 2? What do I get when I multiply 5x minus 2 to the fraction 8x plus 5 over 5x minus 2? I'm talking about this multiplication line right here. Yeah, the 5x minus 2's just cancel. Absolutely. That's exactly the way you'd want to think about that. So what you're left with then is the 2 that's out front and the 8x plus 5. When it distributes to the 5, I'm just going to write that as 5 times 5x minus 2. In the bottom, the same canceling happens when I multiply it to the other fraction. So there I have 5 times 8x plus 5 and minus 8 times 5x minus 2. Dominic? Sure. So far, so good. That was the rough part. From here, it's not so bad. We'll just kind of distribute things through. Does that all look good to you guys? Everybody agree that looks good so far? No mistakes? Jake?
-8 and -2. Positive 16.
Yeah, very good. Remember, we talked about making sure that we're distributing those negatives. I think it was last time that I was going to pull that trick on you a bunch of times. Good job paying attention. That's exactly right. We got to be careful about that. So that should be plus 16 there. Really easy mistake to make. That's why I'm going to do it all the time and then ask you, is this right? And hopefully trick everybody except for 1 or 2 people. And then the next time maybe it'll be 3 or 4 people catch it. And the next time it'll be, and before we take the test, maybe half of us will be able to catch that on a routine basis. And then we're doing pretty good. All right. Combine some like terms at this point. So 16x and 25x is 41x. And then 25 and 16 is 41. Hey, what do you know there? 41 over 41, that cancels out, and I'm left with just the x. Yes. Bless you. Here's the bummer, though. We're just halfway. We still have to do the other composition. Ugh. This is good algebra review, though, right, guys? Yeah. All right, so h in this problem was 2x plus 5 over 5x minus 8. So we're going to be plugging that into h inverse. So h inverse was 8x, but instead of x, I'm going to write that fraction for h. And then I have plus 5. And then the denominator was 5x minus 2, but instead of x, I'm going to write the fraction 2x plus 5 over 5x minus 8. Woo! It's a tough composition. Now I'm going to multiply the top and bottom by... What do you think? 5x minus 8. That's good. That's what I would use. So again, that's got to distribute. Remember, when it multiplies to the fraction, it cancels with the denominator, which leaves us just any coefficient out front and the numerator. And then just multiplies to the 5, because that's just a constant. Again, cancels with the denominator of the fraction, leaving me with just the coefficient out front and the numerator. And then just multiplies to the constant. All looking good so far? Okay, distribute some stuffs. So what do we get here? 16x plus 40 plus 25x minus 40 over 10x plus 25 minus 10x minus 16, right? No, what's wrong? Yeah, there we go. That's what I'm talking about. Make sure we're distributing those negatives. All right, combine some like terms. So positive 40, negative 40. See ya. Positive 10x and negative 10x. See ya. 16x plus 25x is 41x. 25 plus 16 is 41. 41's canceled. And we're left with just x. Oh my goodness. Mr. Kulik, that seemed pretty rough. Am I expected to be able to do that? I mean, like, I'd probably show up on the homework. I wouldn't put something that in depth on the test, but it's a perfectly reasonable homework question. The reason I wouldn't put it on the test is, like, what I would be trying to test for is, do you know how to verify that two functions are inverses? I can do that without making the algebra awful also, right? If the goal is to check that you understand how to determine if two things are inverses, why make the actual checking of that process, like when you apply the process, just like really time consuming and tedious? Like, why make it a 10-minute problem when it could make it a 2-minute problem? You know? Seems unnecessary to this guy. All right, on to my next one. So again, all the examples we're going to do today, the exact same skill over and over and over again. The only thing that's changing is the function type. So we're finding the inverse. First step is to replace the function notation with y equals. And then we're going to get the x by itself. What's the first thing I'd want to do to get the x by itself here? Add 4 to both sides. Great. Next up would be divide by 3. Very good. You don't want to do the square root yet. You want to wait until you've got that x squared by itself. And now when we square root both sides of an equation, what do we have to be careful about? Excellent. Plus or minus. We're on our A game today. Now be careful when you're writing this square root. Notice how I'm writing that square root very large so it covers the entire fraction, both the top and the bottom. If your fraction or your radical only covers the top, it is not the same thing as this. I would have to mark down for that. Okay? You want to make sure your radical covers, your square root symbol covers the entire fraction. Miriam? Certainly. All right, so the x is by itself. Let's swap those x's and y's. And oh no, what do you notice here? What's this mean? It's not going to be a function. Oh no. That is a bummer. So the question kind of should come naturally. Is there a way to change p of x so that P inverse is a function without really changing, without dramatically changing P of x? Well, let's return and think about this for a second. Our P of x looked like this, right? What did we need to have in P of x in order for P inverse to be a function? P of x has to be 1, 2, 1. Has to be a 1-to-1 function. So the easiest way to identify that was by looking at the graph. So if I went to graph P of x, would look like this. Now this definitely fails a horizontal line test. This is very not 1-to-1. Everybody agree? Horizontal. I saw your face. Horizontal line test. Fails the heck out of that, right? So here's what we're going to do. We're going to throw out half of our graph. We're either going to discard this half or we'll discard this half so that it would then pass a horizontal line test. Notice by discarding either of these halves, the range of our function does not change, right? All we're doing is getting rid of any duplicate y values, but we don't get rid of any specific y value. We're only getting rid of the extra, right? Because we have 2 copies of everything. I'm just going to get rid of 1 copy. Still gives us a full set of y's, right? So what we'll do is we'll dump one half or the other. Doesn't matter which ones you dump. I would dump this half. That's going to make P of X 1 to 1. The way we do that is we add in the condition that X is greater than 0, or greater than or equal to 0, which means we're only looking at this part of P of X. Everybody's okay there? So if I take this as my P of X and I try to find the inverse, what's going to happen now? Well, the steps are going to stay the same, right? I'll add 4. I'll divide by 3. We'll square root both sides. But here's the place where we get some advantage. Notice here, this P of X, our X is greater than or equal to 0, right? Here we have X equals. This is the X from P of X. This has to be greater than or equal to 0. But we're told this X is equal to something plus or minus. Can that happen if it's greater than or equal to 0? Can it be minus? No. So that greater than or equal to 0 allows me to dump the plus or minus. And that then ensures that P inverse is a function. Oops. Now, would I ask you to repeat this on a test? No. How would this come up? Well, if you look at your homework, set. Oh boy, that just really took a minute for that to. And you look at one like number 46. Notice you're given that condition, right? All that's doing is ensuring to you that when you find the inverse, it's going to still be a function, that you can dump the plus or minus. Okay? So that's the point of what I showed you here, is like, why are we including a condition like that on occasion? And it's purely so we can dump the plus or minus and ensure that our inverse will be a function. Does that feel okay? I would not expect for you to do your own domain restriction. That, I think, is beyond the scope of what I'd need you to do. But I would expect you to be able to use one to find an inverse, just like we did there. All right, let's check. Oh, Mr. Kulik, are you serious? Yeah, man, we're checking. So P compose, P inverse, that's going to be P of the square root of x plus 4, or the square root of x plus 4 over 3. So when I plug that into P, that's 3 times x squared, but instead of x, I'm going to write square root of x plus 4 divided by 3. So there's my composition. To simplify this, what's the first thing I need to do? To simplify that, the first thing I need to do. Yeah, so the radical, or the exponent, right? Please excuse my dear Aunt Sally. So the square cancels the square root. What do we do next? Again, we're simplifying. What do we next? Well, I see a times 3 and a divides 3. Those cancel out. And then I have a plus 4 and a minus 4. Those cancel out. And x is by itself. That one wasn't too bad, right? Much better than the previous check. Woo! That previous one, still giving me nightmares. I'm just joking. It's still pretty easy for me, but... All right, same idea here. P is 3x squared minus 4. I'm going to plug that in, so I have the square root of, but instead of x, I'm going to write 3x squared minus 4. And then I have the plus 4, and I have all over 3. Simplifying here, what's the first thing I need to do? What's up? I would not do that. We're simplifying, so I just want to use the stuff that's in the problem. I probably don't want to add something else in. Look under the radical. What's in there? What?
4 to -4.
Yeah. Plus 4 minus 4. Those just cancel each other out. Yes. Now what? I wouldn't do the squared yet. I would divide the times 3 and divides 3, yes. And now the squared can cancel the square root. Kate, if you had wanted to do the squared, canceling the square root first there, this is what you'd have to write next, and the likelihood of getting that right, I think, is lower than just doing the reducing, but it's not wrong to do that, but I think it's like kind of inconvenient, which is why I said I would not do that. I noticed I didn't say wrong, but I want to circle back as to like why I said let's not do it that way. Okay. All right. Let's do some more. Ooh, we are running short on time here. Let's skip this one. Go to these ones. Let's take a look at this one. Ooh, what do you notice that's different about this one than all the previous ones? Well, it's got a fraction, I guess, but we had a fraction with the rational function too. The x is in the exponent. Very good. That is the thing that you want to notice here. All right. So first step is we want to get that x by itself. What should I do? Can I multiply the -1/2 and the 3? Important question. Can I do that? No is correct. Again, to multiply two numbers, either the exponents have to be the same. -1/2 has an exponent of 1, 3 has an exponent of 4x, not the same. Or the bases need to be the same. Well, -1/2 is the base and 3 is the base. Those are different bases, so these cannot be multiplied together. So let's get the -1/2 out of there. We'll just multiply both sides by -2. Everybody's okay there? But how do I get that 4x out of the exponent? What do I have to use? What mathematical operation do I need to use to do that? Does anybody remember? You would have talked about it last year in your Algebra 2 course. What mathematical operation do you need to use to get a variable out of the exponent?
Don't you like that little top part, like that one?
The answer starts with the letter L. You need a logarithm. You need a logarithm. Now, how many different kinds of logarithms are there?
4.
Infinitely many. You want to be careful and make this as easy as you can. So you want to choose the logarithm base to make this problem as easy as possible. The base of my logarithm, I want to choose to match the base of my exponential. In this case, that would be 3. Log base 3 is what I would do to both sides. So why did I choose log base 3 as opposed to the natural log or the common log or log base 2 or log base 17 or log base whatever? Because log base 3 will cancel with exponent base 3, and that eliminates the logarithm completely on the right-hand side. I could use any log to do this. I could use any log to do this, but the details get a lot messier. I am in the habit of making my life easier if I have the choice. Here I do by choosing to use the log base matching my exponent base. The simplification on the right-hand side is really nice and neat. If I don't choose that, it gets a little messier, and I'm going to choose to make my life easier. My next step is to just divide both sides by 4. I'm going to write it as a times 1/4 out front, just for clarity's sake, because I want to make clear that that 1/4 is applying to the entire thing. If I write like over 4, sometimes it's unclear if I'm writing over 4 just to the stuff to the inside or to the entire thing. By putting the 1/4 out front, that should make it really clear that it's applying to the entire logarithm. So then I can rewrite this in function notation and swap the x's and y's. To get this, I'm just going to check one side here in the interest of time. Again, because we're starting to run a little bit short. So g is negative 1/2 3 to the 4, but instead of x, I'm going to write 1/4 log base 3 of negative 2x. So if I simplify, the 4 and the 1/4 cancel out. Exponent base 3 cancels log base 3. Negative 1/2 cancels negative 2, and we're left with just x. I'm going to skip the other half of this in the interest of time, because I have one more example that I still want to look at, and I don't want to burn up all my time doing these composition things that are kind of all the same, just the algebra is a little bit different. All right, last example here. Find the inverse for h of x equals 5/3 ln 7x minus 1. What the heck does ln mean? That's the notation for natural log. What is the base for the logarithm natural log? It's not 10. Log's not a number. E is correct. E is the irrational number, 2.71, yada, 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 kind of like pi. So natural log is log base E. So to get the x by itself, I'm going to start by multiplying both sides by 3/5 to get the logarithm by itself. And now to cancel log base E, I need to use exponent base E. So notice I'm going to write that exponent base E comically large so that it's really clear that I'm not multiplying both sides by E, but rather I'm making E the base of the exponent on the left side and the base of the exponent for the right side. Exponent base E cancels log base E. Now to get the x by itself, I'm going to add 1 and divide by 7. So here my h inverse would be e to the 3/5 x. And I want to be clear. I want to make sure that it looks like that plus 1 is not in the exponent. Right? It's being added to the exponential, but not the exponent. And that's going to kind of close off where we are today. I'm not going to do the check here because I only have 3 minutes left. I'm going to get interrupted about a minute. I have one other thing to say. Section 1.7, now closed. Should be able to do up to 56. We are not doing section 1.8 at this time. We're going to circle back and do it when at a more natural location of where it builds on the things that we're going to be doing in trigonometry. This is the last section of chapter 1 that we're covering, which means what's happening soon? Chapter 1 test. Tentatively scheduled for first class day next week. Tuesday, I think. I will talk one more second after this is done.
When we pray, we ask God for help in everything that we do. The Lord says, do everything in dependence on me. The desire to act independently apart from me springs from the root of pride. Self-sufficiency is subtle, insinuating its way into your thoughts and actions without realizing it. But apart from me, that is nothing of eternal value. Use your freedom wisely by relying on me constantly. Thus you enjoy my presence and my peace. Amen.
1 second, though, one
Have
thing.
a great rest of your day. Teachers, you may dismiss it. You're ready.
So reminder, for your test, what do you guys get to have? Half sheet of notes. Start on it now, right? You have to turn those in before the test. I have to have it before the test get passed out. So if you need time to work on that and think about it, kind of start thinking about it and start putting something together.
So wait, those are due Thursday?
Ideally, yeah. End of class Thursday,
And so
ideally.
a half sheet of paper,
Front and back.
Front and back, okay.
Yes, fill it up.